Thanks everyone. This is Rifat Sipai from Northeast University, Department of Mechanical and Industrial Engineering. And in this short demo, what I would like to do is to demonstrate to you how the actuation force or the input to the plant that you're trying to control will be affected by the design of PID gains and how aggressive you want these gains to be. So what I'm going to do, actually, I'm going to just modify this transfer function a little bit so it doesn't look exactly like the one in the homework. So let's just maybe change these numbers. I say this is 10 and let's say this is 0.2. And so we have it's not no longer an MCK dynamics. So this is actually a mechanical system with inertia J and viscous damping B, free to rotate. So the displacement here is angular displacement, at least in the context of the problem we are looking at. And because I am recording this for a homework that I'm that we are designing, and so therefore the focus is on angular displacement. And to be able to achieve angular displacement, we'll be applying torque to the system, and torque goes in and angular displacement goes out. What I would like to do is, however, I would like to actually split this into two parts. And what I want to do is I want to remove the 1 over s factor from the first block. So what I will do is I will actually write it like that. And then I'm going to make this a 1 over s. Like that. Okay. Effectively, it's the same transfer function. When they're multiplied back to back, we have the same effect, right? But by doing so, I split them. Their multiplication remains the same as it was before when they were actually combined together, right? And now this is no longer J and viscous damping, but this is actually angular displacement omega to angular displacement theta. We are integrating, right? And this is the part where we have from torque to omega dynamics. Okay, so the first transfer function shows us how the torque will be converted to angular speed, and so this is omega. And the second transfer function 1 over s will then integrate omega to give us angular displacement. The reason I split these two is as follows. What I would like to compute is the power, mechanical power. And to be able to do that, I need to multiply torque with angular speed omega. In the previous version, when these two transfer functions were actually combined together, omega was not really visible, only angular displacement was visible. And so by splitting these two transfer functions, I revealed an intermediary variable, omega, which I really need to actually compute the power. And so torque times omega is going to be power, so I need a product, and that should be in math. And let's go and find the product. And grab it over here, and I'll rotate these, Control R. It's just going to be more convenient to wire this. Torque times omega, I'm going to multiply them, and that will give me power. And I can then plot this as a function of time. Okay, this is now power. And this we can maybe call it theta, angular displacement. Good. So now what I will do is I'll run this for some PID gains, and I'll try to get a sense of what the power really looks like. So what I will do is I'll do one aggressive, one non-aggressive behavior in the controller. So one controller will apply very aggressive torque values to correct the behavior, and that will come at a price of increased power. And then I'm going to actually readjust the PID gains to make them less aggressive, and they will lead to less aggressive torque values, and that should lead us to see lower power requirements. And this way you will get a sense of the trade-off between how aggressive you want the controller to work and what the price to pay for that. All right. So right now, I don't know what PID gains I need, but if you have already watched the PID tuning, you know what I'm going to do. So I'll tune the PID gains. And as a starter, maybe I will tune these gains to give me a less aggressive behavior. So right now, the tune block in solid curve, right, gives me a settling time of about 400 seconds, right? So I'm gonna actually give you two really polarized examples, so to speak, so you can clearly see what's going on. So now the solid line, we are looking for the solid line to be our new design, which will have about 400 seconds of settling time. All right, let's update that. And then we can put this down for now, and then we say, okay. Now we're gonna simulate this and theta value, and we should see what we have designed for, right? About 600 seconds settling time, and we get that, right? Like 600 seconds to settle from 0 to 1. So in this case, 1 is in radians, so it actually goes from 0 to 1 radians of displacement, angular displacement. That's about 60 degrees, right? It rotates 60 degrees from the initial position. Okay, so now let's take a look how much power this operation demanded, and let's auto scale this, and just pay attention to the scale here. This is 10 to the power minus 4, so this is 0.5 milliwatts and the maximum power, and now we at least have an idea, right, how much maximum power we need for this operation. Nothing more than 10 to the power minus 4. Right, the negative quantity just shows that the direction of the force is changing or the torque is changing. So if you wish, you can take the absolute value if you just want to work with the positive quantities. And all right, obviously this is a very slow operation, right? It takes 600 seconds, right? It takes 10 minutes to sweep 60 degrees. And now we are wondering, all right, what's going to happen to this if I want to be really aggressive? All right, why don't we go and find PID controllers that will give us a more aggressive behavior? So let's look for a response time that is much, much faster. In this case, it gives me 13 seconds, 11 seconds, 9 seconds. Okay, let's say maybe 10 seconds, right? About, let's say, settle around 10 seconds, right? And so that is significantly faster than 600 seconds that we had before, right? Let's look at the parameters, right? Obviously, the gains have changed, right? If you take a look, the proportion gain has increased about 100 times for this to work, right? The integral gain has also increased. It was almost 0, and now it's slightly larger than 0. And the derivative gain has also increased quite a bit, right? About 6 times for this to work. And in return, we're going to get now 60 seconds of settling time instead of 400. And the overshoots haven't changed significantly. So let's take a look what's going to happen now. All right, let's update the block, close that, apply the settings, and run the simulation. Let's just double check if you're getting what we're supposed to be getting. Yes, indeed. I can stop this. There's no need to run this any longer. And the settling time should be around when the response reaches 0.98 or 100, 102, right? So 2% criteria, the settling time is around here, right? It's about 60 seconds. All right, so this is 10 times faster than what we had before. It was 600 before, right? So now let's take a look how much power this required. Now, if you zoom in here, we can see the maximum power. It looks like it's on the positive side. So now the maximum power is 0.11 watts. So now we jump from 510 to the power minus 4 to 0.1. And so that's quite of a jump, right? It's about 2,000 times, I think, jump, if I'm not mistaken, from what it was before. And so sorry, 200 times, I think. And we can clearly see how the power requirement will jump as the control actions themselves demand a more aggressive behavior. Now you may say that, well, 0.1 watts is not a big deal, it's not a huge power, but the idea is to give you a relative jump from one configuration to the other. So as you are handling potentially larger, heavier structures where J can be much larger, right? And if you want to move this, large inertia, right, and from one point to another in a very short amount of time, you will require significantly more power, and that's something you need to keep in mind because your actuator may not be capable to draw that much power to be able to deliver what you need it to do, right? So in the simulation environment, you may not recognize that, you may not realize that because the simulation doesn't know what actuator you're using, but you should be aware of the limitations of the actuator that you're using if you have already one, or you should use simulations like this type to figure out what power levels are needed to complete the operation so that you can go and shop for a particular actuator that will handle those power levels. And that was the main goal of this demonstration. I hope you liked it. Thank you so much.